Hello. Hello everyone. Good afternoon. So let's start the tutorial today. I have prepared something for fun for you, so you don't need to worry about whether this will appear in the exam. So it won't. Today we will talk about an interesting theorem called Bertrand's postulate. So what is it? So Joseph Bertrand, a mathematician, conjectured that for any n, integer n, greater than 1, there will always be a prime between n and 2n. So actually, the statement is it doesn't include n and 2n. But if you want to make this to be inclusive, then we can start from any n greater than or equal to 1. So for instance, between 5 and 10, you can find a prime. Let's say 7 here. Between 10 and 20, there will always be a prime. So let's say 10 and 20, we can find 13 as a prime. So in general, for any n, so let's say n is 100, then between n and 2n, in between them, no matter what happens, there must always be a prime. Okay. This theorem was first proved by Chebyshev, and later there is a shorter but more advanced proof by Ramanujan. Today we are going to look at a proof by Paul Erdős, and then this proof is something that we call elementary. So everything we can know is actually very simple. So we just need to know induction technique and counting. Yeah, that's all. Okay, so we can prove that this is true. Okay, before we prove this postulate, there are a couple of basic lemmas that we want to introduce. And then all of them are quite easy in the sense that we can prove that easily. Although the lemma itself may not be easy, okay? So here, the first lemma we are saying that is, if we are given any real number x, which is greater than or equal to 2, so let's say x is equal to 7, when we are multiplying all the primes that is smaller than or equal to x, so this is the product of p is a prime number, where we are arranging p for all the prime numbers that is less than or equal to x, then the product cannot be that large. It is smaller than or equal to 4 to the power x minus 1. So this is true for any real number. So we can have x is equal to 7.7, 7.89, something like this. So how can we prove this? So we are going to use this later, but then we are going to prove this now. So how can we show? Okay, now the proof idea, so this is what we want to show. We are going to show this by using induction. Now, first of all, we notice that we don't need to prove for all the cases of x. We just need to prove the case where, so for any x that we are going to look at, we can first find out what is the largest prime, let's call it q, that is smaller than or equal to x. If this is true, if the product of all the primes less than or equal to q is less than or equal to 4 to the power q minus 1, then in that case, this product of primes will be the same as the product of primes that is smaller than or equal to x. Is that okay? Yeah, because q is already the largest prime. And then we know that because q is smaller than or equal to x, so 4 to the power q minus 1 will be smaller than or equal to 4 to the power x minus 1. So if this part is true, then we know that the original formula is true. Okay, so first of all, this one is true when q is equal to 2. Yeah, because when q is equal to 2, the left-hand side is equal to what? So the left-hand side is we are multiplying all the primes less than or equal to 2. So this is equal to 2. And the right-hand side is 4 to the power 2 minus 1, which is equal to 4. So 2 is less than or equal to 4. Now when q is equal to 2 is true, then in that case, we know that all the primes, no, not all the primes, all the real numbers that is more than 2 but less than, strictly less than the next prime will also be true. So the original formula will be true for x is equal to 2.7, 2.8, 2.9999. So for any x that is between 2 and 3, smaller than 3, this is also true. Okay, now we need to have this one because although we want to show that the formula is true for all prime q, but since we are using induction, we need to have the induction hypothesis. So when we are proving a certain number, a certain prime q, we assume that all the all the values of x smaller than q will also be correct. Okay, so this is the idea. Okay, so this is the basis case for our lemma. So the next one is, so suppose that for other primes, so other primes, it must be a odd number, right? So for all the primes q, which is of the form 2m plus 1, this is an odd number. Then let's examine what is the product of all the primes less than or equal to q. So for this one, we can separate the product into two parts. We collect all the primes that is smaller than or equal to n plus 1, and then all the primes that is between n plus 1 and q. Now notice that the first part, we can because n plus 1 is a number that is strictly smaller than q. So we can use induction hypothesis to know that. So we can plug in n plus 1 here, so that we know that the product of this one is smaller than or equal to 4 to the power n plus 1 minus 1. So it is 4 to the power m. So this part, this product is less than or equal to 4 to the power m. And for this part, interestingly, we will see that this part is smaller than or equal to 2m plus 1 choose m, this number. Now the reason is that the number here is 2m plus 1 factorial divided by n factorial and n factorial. So we know that what we can cancel is something that is smaller than or equal to m in the from the denominator. So all the prime numbers that is strictly greater than or equal to n plus 1 will not be cancelled. So that means that when we have 2m plus 1 factorial divided by n factorial and n factorial, all the prime numbers that is inside this range will remain here. So that this one will be a multiple of all the prime numbers that is in this range. This could be much larger than the multiple of them. There could be other values. But in any case, this number is large enough to contain all the prime numbers that is inside this range. Now, this is an odd number. So we know that, so 4m, 4 to the power m here, we keep it. So 2m plus 1 choose m. We know that, we know what? We know that 2m plus 1 choose m will be the same as 2m plus 1 choose m plus 1. And then each of them should not be, they're the same, right? And then if we sum all these binomial terms of 2m plus 1 choose 0, 2m plus 1 choose 1 up to 2m plus 1 choose 2m plus 1, then we will have 2 to the power 2m plus 1. So in that case, 2m plus 1 choose m will be at most half of this sum. The half of this sum will be 2 to the power 2m. Is that okay? So somehow, by doing this kind of reasoning, we will find that this value is less than or equal to 2 to the power 2m. So after simplification, 4 to the power m, 2 to the power m is 4 to the power 2m, and 4 to the power 2m is exactly 4 to the power q minus 1. So what does that mean? So in that case, as long as all the values less than q, a certain prime q, they are proven to be correct, then for a particular prime q equals to 2 to the power 2m plus 1, then the formula, this formula that we want to show will be true. So here, this is proven to be correct by using induction. Okay, so I'm explaining this perhaps a little bit fast, but don't worry. So everything is simple, so you can find some time to verify the details again by yourself. So this is lemma 1. We'll have lemma 1 used later. Okay. Next, okay, we have another lemma. This lemma is proven by a French mathematician Legendre. So here, this is stated like this. So let us consider the factorization, the prime factorization of n factorial. Okay. Now suppose that this n factorial is divisible by a certain prime factor p. Then how many times p will appear in the factorization of n factorial. So for instance, when look at, let's say when n factorial is equal, when n is equal to 9 factorial. So how many times we will find the 2, how many times we'll find the 3, and so on and so forth. So we see that for 9 factorial, how many times that we see a 2? Because we know that 2, 4, 6, 8 will contain a 2, but then 4 and 8 will contain another 2, and 8 will contain another 2. So the total number of 2's that we see in 9 factorial will be 4 plus 2 plus 1. Is that okay? And how about 3? So how many times 3 will appear in 9 factorial? So we will see that 3 and 9 will have a 3, but 9 will have another 3. So there are going to be 2 plus 1 3's. So there are 3 3's appearing in 9 factorial. Now how many times we will see a 5? So 5 only appears in 5. So for 9 factorial, it just contains 1 5 in the prime factorization. And 7, 1 time. Okay, so 9 factorial, it turns out that using the prime factorization, we know that it is 2 to the power 7 multiplied with 3 to the power 3 multiplied with 5 multiplied with 7. So that's it. That's for 9 factorial. So in general, for an n, for any n, the number of times p appears in the factorization of n factorial will be equal to what? It turns out that it is equal to n divided by p plus n divided by p squared plus n divided by p cubed plus n divided by p4 and so on and so forth, taking the floor for each of these terms and adding up together. Okay, so we can have this sums up to for infinite number of terms of k, because we know that when k is sufficiently large, p to the power k will exceed n. And in such a case, n divided by p to the power k, taking the floor, will be equal to 0. Is that okay? Now, why it is true? So, yeah, this is by simple counting. Okay, so we now have Lemma 2, the Legendre theorem. Now, based on Lemma 2, we can immediately calculate how many times a prime factor p appears in the factorization of 2n choose n. Now, we are going to look at this term because this term is related to what we are going to, so this term is important. So we are going to use this term to connect with the Bertrand's postulate. So in particular, 2n choose n, how many times a prime factor p appears? So 2n choose n is 2n factorial divided by n factorial and then another n factorial. So the number of times p appears in 2n factorial will be this term. This is from the previous Legendre theorem. And the number of times that p appears in n factorial multiplied with n factorial, it will be 2 times n divided by p to the power k. Is that okay? So this is again coming from the previous lemma. So combining everything together, so that means that 2n choose n will have p appearing this many number of times. Okay? So it's easy, right? So elementary, as I promised. Now, one interesting thing here is that let us take a closer look of this term. So 2n divided by p to the power k minus 2 times n divided by p to the power k, taking the floor here, we claim that it is either 0 or 1. Now notice that this is an integer. This is also an integer. So after minusing an integer from another one, so this is also an integer. Is that okay? And the value of this is counting the number of times that p appears as a factor. So in that case, it cannot be a negative number. So it is at least 0. Now, let us take a closer look. This term is strictly less than we remove the floor notation. Is that okay? So it is 2n divided by p to the power k. We take away the floor notation. And similarly, 2 times n over p to the power k taking the floor, this term is greater than this term is greater than 2 times n over p to the power k minus 1. So here we remove the floor, but then with minus 1. So this term is greater. So minusing this term is smaller than minusing this term. Is that okay? Now, if you look at this one and this one doing the simple algebra, we find that it is equal to 2. So what does that mean? It means that this integer is strictly less than 2, and it is an integer greater than or equal to 0. So there are only two choices, either 0 or 1. Is that okay? So we go back to the previous slide. So we will see that 2n choose n, this term contains the prime factor p this many times, and this summation is actually summing up a lot of 0 or 1s together. Okay, so maybe 0 plus 1 plus 1 plus 0 plus 1 plus 1 plus 0 and plus 0 and so on and so forth. So it can be something like this. Okay, so immediately we will see that there is a natural upper bound on the value of this one here. So this one cannot be more than so because we see that if k is larger than, if p to the power k is larger than 2n, then this term will become 0. So this one is 0, then this one cannot be anything. So because we need to have, after the minusing term, it needs to be 0 or 1. So if this becomes 0, so everything becomes 0. Okay. So the most times that we are going to have this one to be non-zero is when p to the power k is strictly is less than or equal to 2 times n. So in that case, we can see that 2n choose n contains the prime factor p at most the maximum of r, where p to the power r is still less than or equal to 2n. Now we will use this corollary later, okay, when we prove the Bertrand's postulate. An immediate fact here is that we will see that when p is larger than square root of 2n, then p to the power 2 will already be greater than 2n. So it means that the r value can be at most 1. So when p is larger than square root of 2n, the value here, this one, will contain only at most 1 time of p. Okay? So we are nearly ready to prove Bertrand's postulate. So before we move on, then let us take a look of 2n choose n again. So we claim that 2n choose n doesn't contain the prime factor p whenever p is in this range. So p is in this range, so p is larger than 2n over 3, but p is less than n. So what is so special about this range of values? So this range of values will force, okay, so first of all, when p is in this range of value, p is less than or equal to n, so 2n factorial will contain p 2 times at least. But on the other hand, when p is in this range, we will have 3p is greater than 2n. So it means that the value of 2n factorial, this one will contain multiples of p less than 3 times. So it contains multiple of p at least 2 times and strictly less than 3 times. So what does that mean? It means that 2n factorial will contain exactly 2 numbers that is divisible by p. So which are the 2 numbers? One of them is p and the other is 2 times p. Is that okay? On the other hand, n factorial will contain exactly 1 number divisible by p. Yeah, because p is in this range. So 2 times p is already more than n, so it cannot have 2p less than n, right? So what does that mean? 2n factorial contains 2 numbers divisible by p. N factorial contains 1 number divisible by p. So 2n choose n is 2n factorial divided by n factorial. So there are 2 numbers divisible by p, 1 number and then another number. So they cancel each other. So it means that this whole number doesn't have p as a factor. Okay? Okay, so we are nearly done with everything. Okay, so we are ready to prove why Bertrand's postulate is correct. Now, as usual, in order to show that it is correct, we are going to use proof by contradiction. So we assume that it is wrong, and somehow we hope to get some nonsense coming out. So we assume the postulate is wrong, and now consider our number 2n choose n, because we are focusing on this number. This number will be special, okay? Now 2n choose n, first of all, we claim that it is less than or equal to, so first of all, it is equal to the product of p less than or equal to the square root of 2n p multiplied with the product of p in this range multiplied with the product of p where p is in this range. Now notice that this range is not a full range. We have p less than or equal to square root 2n, p is between square root 2n and 2n over 3, and then p is between n and 2n. So we have missed a range. The range is when p is between 2n over 3 and n. The reason is that it is by lemma 4 that there is no factor of p in the range that we are missing. So in that case, we don't need to consider the range. But now, how about the product of the prime p, where p is less than or equal to square root of 2n? Now, when p is less than or equal to square root of 2n, then what will happen? So when p is less than or equal to square root of 2n, then we will see that we are going to have at most r copies of the prime p such that p to the power r is less than or equal to 2n. So that means that for each p that we consider here, if we multiply all the copies of it, then it is no more than 2n. So we are using 2n as a bound, as an upper bound, to bound the product of p, where the product of the number of times that p appears, so p may appear 5 times or 2 times or 7 times, whatever, but then for any p that we look at, all the prime factors, all the prime powers of this p, when they multiply together, will be less than or equal to 2n. So we use 2n to replace it. So this part is 2n. Now for this one, this one is p is within this range. So this is p is greater than square root of 2n. So when p is greater than square root of 2n, then this prime p can appear with at most 1 copy. So we just multiply with p here. So this is also the case where p is greater than square root of 2n. So we just have p to the power 1 here. Okay, but next, okay, so I copy the same formula again. We can find some simplification of these terms. So for the first term, so because each one is 2n, it is independent of the prime p that we are looking at. So the product of all the numbers here is less than or equal to 2n multiplied with itself square root of 2n times. So we just assume that every number smaller than or equal to square root 2n, they are primes. So obviously it is not, but in that case, this is an upper bound of this value. Is that okay? Now for the middle term is we are multiplying all the primes that is inside this range, but then all the primes that is less than or equal to 2n over 3. So for the middle term, we can apply lemma 1. Lemma 1 is we are multiplying all the primes less than or equal to x. It is smaller than or equal to 4 to the power x minus 1. So here, we just make everything sloppy. So we claim that this is smaller than or equal to 4 to the power 2n over 3. And finally, we are multiplying all the primes that is inside the range n and 2n. Because we are proving Bertrand's postulate, and then we are assuming that it is wrong. So in that case, there is no prime between n and 2n. And because of this, the product of this one is 1. Okay? Yeah, we use a 1 to represent the general case. Okay? Okay, now we have one more thing. So 2n choose n. we claim that it is greater than or equal to 4 to the power n divided by 2n. The reason is that this is the binomial term, and then the sum of 2n choose 0, 2n choose 1, and so on and so forth, up to 2n choose 2n, it adds up to 2 to the power 2n, which is 4 to the power n. While 2n choose n, this is the middle term of the 2n choose anything, is the largest term. So in that case, the sum is 4 to the power n, and then, yeah, actually we can have 2n or 2n plus 1, no matter what happens. So this is roughly this number. So this value will be greater than or equal to the average term. So it is greater than or equal to 4 to the power n divided by 2n. Okay, you can make this 2n plus 1. It doesn't make anything a little wrong, but yeah, it should be okay anyway. So 2n choose n. Suppose that it is true. It is greater than or equal to 4n divided by 2n. So in that case, this term is greater than or equal to 4n divided 4 to the power n divided by 2n as a whole. So we can have a new formula. So we will have 4 to the power n divided by 2 times n will be less than or equal to this one multiplied with this one. So after rearranging the terms, we will see that we get 4 to the power n less than or equal to 2n to the power something plus a constant plus 3 times square root of 2n. Now we notice that this term is going to be much larger than this one when n is sufficiently large. To see this, okay, it is difficult to see because it is a constant to the power n, but this is n to the power something, right? To see why this is going to be larger asymptotically, we can easily see that by taking the log on both sides. When we take log on both sides, the left-hand side is n times log of 4. The right-hand side is something like square root of 2n times log of n, so of that order. One is n, the other is square root of n log n. So we will see that the left-hand side will be much larger than the right-hand side as n gets large. So what does that mean? So it means that when n is sufficiently large, all the things that we derive here will lead to a contradiction because the left-hand side cannot be smaller than or equal to the right-hand side. So at this moment, we know that Bertrand's postulate will be true for sufficiently large n. Here, after some calculation, we find that when n is 4,000, it is sufficiently large to make the left-hand side not smaller than or equal to the right-hand side. So Bertrand's postulate, at least we now know that it is true when n is large. So n is larger than 4,000. But how about the other case? Now the other case, we can see that, so we are going to use brute force method. We enumerate a couple of primes that is less than 4,000. So we find that 2, 3, 5, 7, blah, 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 up to 4,001, they are all primes. Now, the reason that we are choosing these as primes is that because between this one and the next one, the next one is less than 2 times the previous one. So what does that mean? So it means that if you find any n that is less than 4,000, let's say n is equal to 200, then we will see that 200 is between 163 and 3. Okay, so when n is equal to 200, then we will see what? We will see that 200 is here in this range. So the number 317 will be less than 2 times of 200. So for any n that is smaller than or equal to 4,000, it is going to be one of these numbers or in between the values of one of these numbers. So that we will see that there is always a prime less than 2 times of n. So Bertrand's postulate is also true for other values of n. So by contradiction, we show that Bertrand's postulate is true for large n, and by brute force enumeration, we find that Bertrand's postulate is true for the remaining unconsidered n. So together, when we combine them, Bertrand's postulate is true for all cases. Okay, so this is a very interesting theorem. So although it doesn't look easy to prove from the beginning because primes doesn't have any pattern. Yeah, there can always be what? There can be always be a very large gap between two successive prime numbers. But in any case, for any value and the two times of that value in between, there must always be a prime. I hope you like it. So this is what I want to show you today. Okay. Yeah, thanks all. So this is all for today. And then on Thursday, we will continue with the homework 6 solution. And then next week, we have only next Tuesday for the exam, and then we don't have any Thursday class. So wish you all good luck for the exam. Yeah, and if you have any questions, yeah, please remember to send. So perhaps I'm not going to check the questionnaire very regularly. If you have urgent questions that you want to ask, yeah, please send it to the announcement to the group discussion board, or send the direct emails to me or the tutors. Yeah, thanks all. Thank you very much. Okay. Okay. See you.